All right, good morning. Good morning, everybody. So here we go. More discussion about probability. And again, probability is one of those concepts where there are parts of it that are very easy to understand, and then it gets complicated quickly. So it takes more work to get used to than it appears at first, right? And you can get into situations that get fairly complicated. And this is why most people who haven't actually learned probability in, like a class like statistics or something, tend to do probability incorrectly, right? Once you understand probability, you'll see people using it wrong all the time. In fact, I would say more often than not, when I hear just like a non-math person say the word probability, if you listen to what they're doing, their statement that they're trying to make is probably just completely wrong because they're using things incorrectly. Right? They're taking that basic first understanding of probability and trying to expand it in ways where, you sort of don't say anything because you don't want to be rude or you don't want to butt into a different conversation or something, but it's like you sit there and you listen like, oh, this person has no idea what they're talking about. So we've got that basic understanding of probability from last time, right? And understanding there's two types of probabilities. There's the probability with equally likely outcomes. That's if you're flipping a coin. That's if you're rolling a dice. That's if you're pulling a card out of a deck of cards, something like that. All outcomes are equally likely. When you roll a dice, you are as equally likely to get a 2 as a 6. Okay. Same thing with a coin. Assuming you're using a fair coin, then you're equally likely to get heads as tails. Okay, so that's one type of probability. What we did is we counted up the sample space. That is the number of outcomes, and it's important to be able to count these outcomes, right? It can get a little tricky. And then what you do is you look at the number of ways to get the thing that you're looking for. So the probability of getting an odd number when you roll a regular typical dice is 0.5, right? Because there's 3 ways to get an odd, 1, 3, 5, and there's 6 possibilities. That's 3 over 6, 1/2, or 0.5. Okay. Lost my train of thought there. So we looked at the basic intro. Oh, right. And then we had the other type of probability. If you were, it's the final moments of a playoff game and you want to know what's the probability Steph Curry's going to sink this free throw that he's about to shoot, we can't use the same rules. We can't say, well, there's 2 outcomes, he makes it or he misses it, and there's one way to make it, so it's 0.5 that he makes the basket, right? That's different because the likelihood of Steph Curry making a free throw and missing a free throw are not equally likely outcomes. So that has to be calculated with more information. We basically have to observe what happens over a long period of time as Steph Curry is making free throws, and then we can come up with a probability that he'll make that next free throw, right? So you have to kind of separate those, right? It's a common mistake is a person will use one method for the other type of the probability, and then obviously it doesn't go right. So that's good. We got our basics for probability down last time. We're now going to expand. So remember, let me move this over so you can see it. Remember, we've got this scale here. A probability is always a number between 0 and 1. So from 0 to 1. We like, people will talk about chances. They even put that in here, 50-50 chance. You can put it in terms of chances. You can put it in terms of odds. Like a lot of stuff in Vegas, gambling related stuff is done in terms of odds. If you go to bet on a sports game, sometimes at the roulette table, things are done in terms of odds. And I actually think they do that on purpose. I think they do that because most people don't really understand how odds work. And odds are more complicated to use mathematically. So we really want to think about in terms of probabilities, right? The probability is between 0 and 1. And it's tempting to use other language, and sometimes it's okay. We start talking about percentages, and that's okay as long as you realize what the actual probability is, a number between 0 and 1. So why is it such a big deal? Why am I making a big deal out of this where I'm saying, remember always that your probability is between 0 and 1, although we sometimes think about it as percentages, and sure, you could use odds or something like that. Well, what's the big deal? The big deal is that probability is the actual mathematical way of representing the thing that we're talking about, the number between 0 and 1. It's kind of like, I know students get frustrated in algebra when we start learning about percentages, and they want to plug the percentage into the formula, like when we're doing compound interest or something like that, and there's the little R for your rate, your interest rate, and they want to plug in 8 for 8%, but then the decimal you have to plug in is 0.08. The mathematical way of representing that is 0.08. Now, we put it in this sort of like pseudo-mathematical way of representing it called percentages. Percentages are just sort of a way that makes it simple for humans to understand a little bit, but we don't actually put those into equations because they're not as mathematical. They're kind of messy a little bit, right? Well, it's the same thing here. If you're confused, if you're trying to put in you're thinking about it, or you have your rules about when to exclude a p-value or when not to, and you don't have your probability in the right form, right? If we're saying the cutoff for this p-value is 0.05, and you've got things in terms of odds, well, then good luck. You're not going to know what to do, right? Where the mathematical version that we use to make decisions is that a probability is a number between 0 and 1. Now, sometimes when you calculate a probability, you'll end up with a fraction. And I know all through your algebra classes, we always had you leave things in terms of fractions. This is one of those cases where we say, go ahead and put it in terms of a decimal number, right? Because then we can round a little bit easier. It's a little harder to round a fraction. What does that even mean? But if we put it in a decimal, we can round it. So like, for instance, right here, you can see in this problem, this is a problem about smokers. So they, what do we have here? There's 808 non-smokers and then 202 smokers. So that means a total of 1,010 people. That's another thing I want to point out. You can find information in the problem that isn't, oops, I just messed this up. I clicked a button on my mouse and it messed everything up here. Where was I? Oops. Right there. Sorry about that. Remember, once you get comfortable with these probabilities, you can figure out information given in the problem, or you can figure out information that isn't given in the problem. So, for instance, if you know there's 202 people that smoke and 808 people who don't smoke, maybe in the problem you're not given the total number of people surveyed, but you know what it is. It's 202 plus 808, 1,010. So, if you ever feel like you're missing a piece of information, look in the problem and ask yourself, can I figure it out by looking at things? Can I kind of get that information? So then they use the fraction that we talked about before, right? 808 people over 1,010 were non-smokers. But those numbers are not exactly like, they're not round numbers, right? So what we do is we put it in decimal form, and since most of us, hopefully at this point, are comfortable about thinking about decimals in terms of percentages, we go, oh, so that's about 80%, right? Again, percents are not like a highly mathematical way of doing things. The decimal is a more mathematical way of doing things, but it helps us understand. It helps us go, oh, okay, 80% of people are non-smokers, 20% of people are smokers, according to the data that we found, whatever's appropriate to this problem that we're looking at, okay? Okay, so let's get into the new material here. We have the complement. So the complement of event A, denoted by A with a bar over the top, is usually how we signify this, consists of all outcomes in which A does not occur. So it's like the opposite, right? So, you know, it would be like the smoker situation. You're either a smoker or you're not, right? You're either a person, even if you rarely smoke, you smoke, right? So you're either a person who never smokes or you're a person who at least occasionally smokes, okay? There's no like, I kind of smoke. Well, if you smoke, then you smoke. If you don't, then you don't. So you're in one of those two categories. So everything in that, like every person is either a smoker or a non-smoker. And some people might, you know, there's a gray area where people are like, oh, I'm not a smoker. I only smoke on holidays and when I'm at parties. Well, then you smoke, right? So every single human falls in one of those two categories, smoker or not smoker. Those two sets are considered complements of each other. So the complement of smoker is non-smoker, right? Remember we did this in You had this with angles. You probably learned it a couple times. You probably learned it in grade school, and then learned it later in algebra or something, where, the complements of the angle, if you have one angle, the other part that fills in the rest of that angle to make a 90-degree angle is called the complement. Well, it's a similar idea here. It's the two pieces that go together to form the whole group. So if you have the group of non-smokers, then the complement is smokers, right? It's just the opposite group. So we can use that with probabilities, because sometimes what happens is calculating one of those two groups from the information that you have will be significantly easier than the other one. Okay, so there are times when you may want to figure out the probability of something happening, but it may be a very complicated calculation. So what you want to do is, in fact, calculate the complement, the other part, and then that might be easy to do. It might be easier to calculate the complement. So if you take the probability of an event and the probability of its complement, what should those add up to? Well, they should add up to 1, right? Because the highest probability you can have is 1. That's the whole space. If we roll a dice and we look at each outcome and we add up the probabilities of each outcome, they should add up to 1. So a dice, there's a 1/6 probability of rolling a 1, 1/6 probability of rolling a 2, 1/6 probability of rolling a 3, all the way up to a 1/6 probability of rolling a 6. Well, if you add up those 6 1/6 probabilities, what do you get? You get 1, right? So, it's like a coin, right? Let's flip a coin. The probability of getting heads when you flip a coin is 0.5. The probability of getting tails is 0.5. So what happens when we add those together? You get 1, right? Because the coin's not going to land on its side and just balance there like that, right? That doesn't happen. So, what you can do then is calculate the complement of the thing that you actually want to calculate, and then just do 1 minus that complement, and that gives you the probability that you're looking for, right? Because the two events together add up to 1. So if we take 1 minus one of those events, it gives you the probability of the other one. Just like here, we can calculate that the probability of, if you just randomly go out into this population that they sampled, you go out, you just randomly pick someone, there's an 80% chance that they are a non-smoker. So then what is the probability that they are a smoker? 20%, right? Because the complement of 0.8 is 0.2 when we're talking about probabilities. All right, so that's what we mean by the complement. It sounds really like sophisticated, and we're getting really abstract, and we're not. It's not too bad. It just means the leftover piece. Right. Okay. So we start to get into some cutoffs. So at what point do we decide that things are unlikely? Like, at what point, like, how improbable does something have to be before we start to kind of go, something seems a little fishy here? Remember we talked before about this? I give you all have a coin in front of you. You flip the coin 5 times, and somebody gets tails all 5 times. Now, that's unlikely. But it's not, like, again, you're not going to be calling the news and go, can you believe what happened? This person flipped a coin 5 times and they got tails all 5 times. You better come to a story on this. It's not that miraculous, right? But if someone flipped a coin 1,000 times, a supposedly fair coin, they flipped it 1,000 times and got tails every single time. Now all of a sudden we're all paying attention going, what is going on here? The rules of physics don't seem to apply in this room or with this coin. What is happening, right? So the question is, at what point do you start to scratch your head and go, things seem like they're getting a little weird here. This probability seems really low. Like when should we start paying attention? So in probability, there are some normal cutoffs, right? And it depends on what you're doing. Because if we're just, I think I've mentioned this before when we changed the smoking policy on campus. I'm on the academic senate, so we discuss different types of policy changes at school. And, one of the things that people wanted to know when we were discussing we didn't get to make the decision. The president at the time, who's now the chancellor of the district, he made the decision. But we made a recommendation to the president at the time as to what we thought he should do, what his choice should be about the smoking policy. Well, one of the things we wanted to know is, what do students think, right? It would be kind of silly if we went about and just made this decision about the smoking policy but didn't consult the students, right? So we wanted to know, what do the students think about this? Is there a probability that there's enough students on campus who support the smoking, who support smoking, that we need to make sure they have some places where they can go smoke, but it's not like right where everyone else is trying to be. We're trying to make these kinds of decisions. Well, you need to know, like, where's that cutoff where we consider something a low probability, a low percentage, right? So in statistics, we have these sort of typical cutoffs. We've got the 10%, 5%, and 1%. Oh, I forgot the point I was trying to make. The point I was trying to make was the error, because there's always error when you sample, right? You almost never, or you never really even know. Like, what we're trying to do when we sample things in statistics is we're trying to figure out what the body at large, the population at large thinks. So we did a sample. What do you think about smoking policy on campus? Do you want it to be no tobacco at all or no nicotine products at all? Do you want it to be that there are 4 or 5 places on campus where people can go and smoke? Or do you want it to be that people can smoke all over the place, which wasn't really an option because no one's going to support that. But in that case, if we have a little bit of an error there, it's not really a big deal, right? Because if we think that 80% of the school population support a full tobacco ban, and it turns out that it's really 78% of the student population support a tobacco ban, not a big deal, right? Because it's not going to change our decision if we calculated 80% and the true value is 78%. We're still going to go with the same decision, right? But if you're looking at a wing for an airliner that you are designing, and you're going to release, this was something that was been in the news the last few years, is that Boeing has had some issues with safety on some of their planes. There's all these safety protocols in place. So it's really important that you get it right. You want to be real sure about your numbers, because you don't want planes falling out of the sky. Right? You don't want planes crashing, which is a thing that's literally happened in the last few years, where planes were having safety issues. So how do you pick the cutoff that you think is important? Well, depends on what you're doing. Depends on the context. Are lives on the line? Are people's safety at risk? Are people going to get cancer if you get this wrong? If you think it's safe to put something in the water and it's not, are people going to develop medical problems? Those, you want to be real sure what you're talking about. Like you really need to know what your statistics are and be real confident in those. If we're just talking about changing a tobacco policy on campus, sure, we want to be, in the ballpark of the right numbers. But if we're off by 2-3%, it's not going to change our decision. Whether 80% support a full tobacco ban or 78% support a full tobacco ban, that's not going to change the president's decision. The college president I'm talking about, when they make those decisions. So it's like everything in statistics, it's contextual. You have to look at the situation you're looking at and decide what those cutoffs are. So you're going to start seeing these numbers pop up frequently: 0.1, 0.05, and 0.01. Okay, you'll see these like throughout the rest of the course. When we do hypothesis testing, you're going to pick a cutoff level. And the default is usually going to be 0.05. That means that we're 95% confident that our work is correct. Okay, you can sometimes be 90% confident. That would be 0.1, because the complement of 0.1 is 0.9. That's 90%. We could be 90% confident, but that's not real confident, right? That still means you're wrong 10% of the time. If we do 95%, that means we're only wrong once out of every 20 attempts. That's starting to be pretty good. Now, if we wanted to be real careful, we could be 99% confident, right? That corresponds to a cutoff for a probability of 0.01. Okay. Now the question becomes, well, why don't we always just be 99% confident? And the answer is it's as you increase your confidence, you decrease your accuracy. So we'll talk about this idea more when we get into confidence intervals. So basically, to be more sure, our confidence interval has to get bigger, right? Think of it like a target. You're throwing darts at a target. Think about the bullseye. Maybe you're pretty good, so you can hit the bullseye pretty regularly. Maybe half the time you're trying to hit the bullseye, you can hit it. Well, what if we put a dartboard up there where the bullseye was bigger? It was like the size of a fist, maybe, right? Well, then you're going to hit the bullseye a lot more. So you can be a lot more confident that, yeah, when I throw this dart, I'm going to hit the bullseye because it's huge, right? That's how our confidence intervals work. In order to be more sure about them, we have to expand the confidence interval, which means you have a wider zone. It would be like if you asked me when the test was and I said, I think it's going to be next week. Or I could say, well, I'm going to be really confident in my answer and say it'll be in the next month, right? So I'm more confident it will be in the next month, but that's less helpful to you as an answer because now that's more time that it's spread over. If I say, well, I think it's going to be in the next week, I might be wrong occasionally, but you can plan better because I've given you a small enough range that you can go, oh, okay, I can plan for next week. That's fine. If I tell you it's in the next month, I'm probably correct, but you're like, I don't know, is that a week from now? Is it 4 weeks from now? When is the test going to be? It's harder for you to plan. So we have these typical cutoffs that are like the standards in statistics. 0.1 for 10%, 0.05 for 5%, 0.01 for 1%. Most of the time, we're going to go with 0.05. Okay, that's kind of the default, 0.05. And you can use those in your projects and stuff when you're doing your hypothesis tests. If you want to use 0.05, I don't think any of the statistics we were looking at in class are probably life and death, unless maybe maybe you're considering the coronavirus life and death for the. Obviously the coronavirus is life and death, but I mean as far as the questions that you asked and relating them to work and school and stuff like that. We're not designing anything where someone's life is on the line, but you can. You can decide those values as we go. Let's see, where was I? Oh yeah, some basics of probability. So important principles and notation for probability. The probability of an event is a fraction or decimal between 0 and 1 inclusively. That means your probability can be 0, which means that if you're not going to witness that event. Your probability can be 1, which means you're going to see that event occur every single time. Okay, and I know I keep saying this, but believe me, there's a lot of students who will be working on a problem, and then they're shocked to find out that the probability is a number between 0 and 1. They're like, I thought the probability was a percent. No, we can convert our probabilities to percent and talk about them, but the probability itself, the way you use a probability, is a number between 0 and 1, and you have to understand that if you're going to use probabilities correctly. Okay. The probability of an impossible event is 0. The probability of an event that is certain to occur is 1. I kind of just talked about that. The probability of event A is denoted P of A. So remember this notation. The capital P means probability. And then you put whatever event in here. So you would have had to already define what A is. Is A that you get tails when you flip a coin? Is A that you get a prime number when you roll a dice? Could be all sorts of stuff, right? But P of A is how, so you might write, remember last time we did like P of prime. So that since we knew we were talking about dice, then we know, oh, that's the probability of rolling a prime number. The probability that event A does not occur is denoted P of A complement. So remember that bar, that's our complement. So the probability of that event doesn't occur is the complement. It's going to be 1 minus that other probability. Okay. We don't want to get into odds. Right now, you're probably not going to use odds in your project. I forget if there's a couple questions on them, but it's pretty straightforward, those problems. If you have any questions, see me, and we'll talk about it. Okay, then we're going to get into more complicated versions of probabilities. So a compound event is any event combining 2 or more simple events. Okay. So you have 2 events that occur, We now have that compound event, and there's different way that these compound events can take place. Okay, so and here's where our formal addition rule comes into place, right? People mess this up. This is one of the things I'm talking about where people use probabilities incorrectly, right? Because they make an assumption about what they think this formula is going to be, but if you look at this, some of you are probably looking at this and going, what's that piece on the end? Why is that there? That's the piece people assume is not there. So the thing that you have to think about when you're adding up, when you're doing an or statement for probabilities is there overlap between these two groups, right? So we could ask the class, we could survey everybody. How many of you have a job? How many of you currently are working at a job? And how many of you are, let's see, taking a class wouldn't work because that's 100% of you. How many of you are, how many of you eat, how many of you have food delivered at least once a week, right? So we might say, okay, how many of you have a job? Okay, it ends up being 0.8. So the probability of selecting someone in this class that has a job is 0.8. All right, how many of you have food delivered once a week? All right, maybe that's 60%. So maybe 0.6 probability. So the logical thing is to think, oh, well, if I want to figure out the or, I just add the two probabilities together, right? Well, try that. We would take the probability that you have a job, 0.8, plus the probability that you get food delivered once a week, 0.6. I add those together, I get 1.4. 1.4 is not a probability. A probability has to be a number between 0 and 1. See, this is one of the reasons we stress talking about probabilities between 0 and 1, because as soon as you get a probability above 1, a little light bulb should go off and you go, wait a minute, something's wrong here. This isn't working the way that it's supposed to be. So why didn't that work? Why didn't it work? Because it seems reasonable. Why can't I just add those probabilities together? The reason is that we are double counting some of you. There are some of you that have a job that also have food delivered once a week. So you got counted in the first group where the probability was 0.8, and you got counted in the probability in the second group, which was 0.6. We double counted you because you were in both groups. Okay, so that's why that probability got to be more than 1, because some of you are in the intersection. That means that you're in both of those groups, right? So that's why we have this piece on the end. It says, in order to figure out if we wanted to know the probability that you have a job or the probability that you get food delivered once a week, we would take those two probabilities separately and we would add them together, but then we would subtract off the overlap. We would subtract off the number of you that said yes to both of those things. That would give us the true probability. Okay? So that's why they talk about this intuitive addition rule, and it doesn't work. That's where people usually mess up. The intuitive addition rule works if your two groups are totally separate, if there's no overlap, but that's just the same as this value here being 0. So just always think about this formal addition rule. Sometimes this piece on the end will be 0, right? So for instance, if we did things that could not overlap, so how many of you were born in Canada, right? So what's the probability of being born in Canada? And then how many people were born in, say, Mexico, right? Well, you can't be born in Canada and Mexico. You're in one or the other. Those are disjoint. So all we'd have to do is add the probability of being born in Canada to the probability of being born in Mexico, and then we have the probability of being born in Canada or Mexico, right? But there's no overlap. You're born in one of those separate countries. So then that would mean that what's the probability of people that are born in Canada and Mexico? Well, that would be 0 because you can't be in both of those, right? So in that case, it's an easier calculation, okay? So that's where this definition comes in. Events A and B are disjoint, or another term is mutually exclusive, if they cannot occur at the same time, right? You cannot be born in Canada and also be born in Mexico. You were either in the location of Canada when you were born, or you're in the location of Mexico. You can't do both, right? So So actually, here's a good picture for those of you who have seen Venn diagrams before. If you have two groups, A and B, there are going to be times when you have an overlap. Like, blue is the people who have a job, yellow is the people who have food delivered. There's a group in the middle who are working and have food delivered, and they got double counted. Or we have this situation. We have the group of people that were born in Canada, the group of people that were born in Mexico. There's no overlap because you're not in both of those, or you can't be in both of those groups. It's one or the other, right? But not both. Okay. So think about those Venn diagrams. This piece, so here's they actually do a good job describing this right here. This is the probability of A occurring, the blue piece. This is the probability of yellow, the B occurring, the yellow piece. And then what we have to do, since this kind of beige, well, I guess it's not really beige. I don't know what you'd call that color, kind of a gross teal or something, like a faded out teal. We counted that with the A group and we counted that with the B group. So we subtract off this amount once, and it takes away that double counting. This is a thing that, I'll explain it and students are totally like, yeah, that makes total sense. And then when they go to do the homework, they just add up the two values separately. And they don't, and then not every student, but like a good percentage of the students, they make that mistake. They forget the overlap piece. So make sure you're paying attention to that. Right. And then here's what I was talking about before. If we add up the probability of complementary events, they add up to 1. So if you know the probability of an event, you can figure out the probability of its complement by taking 1 minus the probability of that event. So if you know the probability that something occurs, you get the probability that it doesn't occur by taking 1 minus that amount. Okay. So here's the example that they give us. Based on data from a Harris Interactive poll, the probability of randomly selecting someone who believes in the devil is 0.6. So the probability that they believe in the devil, right, there's our notation, equals 0.6. If a person is randomly selected, find the probability of getting someone who does not believe in the devil. Well, then you would just take 1 minus the probability that someone believes in the devil. Whatever that number is, that's the probability that the people don't believe in the devil, right? So 0.4. So 1 minus 0.6 gives us the opposite 0.4. That's the opposite event. Okay. Let's see how we're at time. Okay, we got a little bit of time left. Let's keep going. As always, if there's any questions, throw them in the chat. Okay, then we get into the probability of A and B. So remember, the discussion we just had was the probability of A or B. So that was the probability, or means that one thing happens or the other thing happens or both. This, in math, we have what's called the inclusive or in math and statistics. In everyday life, we have the inclusive or and the exclusive or. And most of the time, people don't think about it. Like when someone says the word or, you don't go, wait, stop. Are you using the inclusive or the exclusive or? Sometimes you do have to ask. But most of the time, you pick it up from context, right? So technically, or means A or B or both A and B. That's the mathematical way that we approach it. That's called inclusive because you can include both of them. There's also the exclusive or, but you pick this up from context when people are talking to you, right? Your friend says, hey, it's your birthday today. Do you want me to take you out to lunch or do you want me to take you out to drinks after dinner? You probably are not going to respond with, oh, I'd like you to do both of those, please. That would be considered rude, right? Your friend's trying to do something nice for you. They're saying, do you want this or this? You just pick one. You don't want to come off as greedy or taking advantage of your friend. So it's sort of understood you just get to pick one of the two. That's the exclusive or. A or B, but not both A and B, right? That's sort of the greedy part. So when we talk to each other in normal language, we just, without even thinking about it, we pick up whether it's an inclusive or exclusive or. In mathematics, we mean inclusive or. Now we're looking at the and. So that means that both things have to occur. So before, I asked about the probability that you work or the probability that you get food delivered. Okay, now that's very different than if I say, let's calculate the probability that you work and get food delivered, right? Then you have to satisfy both of those conditions. That's what the and means. You're satisfying both of those conditions. Which one would you expect to be a bigger probability, the or the and? Just think about it for a second. The or should be the bigger probability. The and should be the smaller probability. It is possible for them to be equal under certain circumstances, but the and is more restrictive because you have to meet both conditions, whereas for the or, you're just looking at the groups that the two groups that have one or the other, and you're combining those together, right? So we have the probability of A and B. Probability that event A occurs in the first trial and event B occurs in a second trial. So you're basically looking at what is the probability that both of these things occur. And this is a type of compound event and can come up frequently. Okay, so there's this notation that frequently gets used. We have for the probability of B, line A, represents the probability of event B occurring after it's assumed that event A has already occurred. Okay, we interpret that line as meaning sometimes it gets filled in with given that. So the probability of B occurring given that A has already occurred. So if you know that A occurred in trial 1, now what's the probability of B occurring in the next trial? Okay. Yeah. Okay, so here's our definition. Two events A and B are independent. This is different than the definition we learned a minute ago. If the occurrences of one does not affect the probability of the occurrence in the other. So remember before we were talking about exclusive, that is the two sets were separate from each other. This is different. Sometimes students mix up these two definitions. The one we talked about a minute ago for mutually exclusive or disjoint versus independent. Not the same thing, but they kind of sound similar when you hear them. Two events A and B are independent if the occurrence of one does not affect the probability of the occurrence of the other. Several events are similarly independent if the occurrence of any does not affect the probability of the occurrence of the others. If A and B are independent, they are said to be if A and B are not independent, they are said to be dependent. Okay, so think of it this way. Remember and this is actually not intuitive for a lot of people. Remember we talked about roulette the other day? Right? And there's this idea of people walking by the roulette table and they look at it and they go, okay, the black numbers have come up 6 times in a row. Red is due. I'm putting my money on red. But remember, those past events do not affect the next roll of the dice. The roll of that little ball on the roulette table. That ball isn't going round and round and going, all right, I just fell on a black number 6 times in a row. I better make it a red this time. Right? It doesn't remember. The likelihood of those past events does not change that next one. They are independent, right? Same thing with a coin. If I flip a coin, the coin doesn't have a memory. The coin's not keeping track of things and going, man, I just came up heads 10 times in a row. I better make it tails this time. If you flip a coin 10 times in a row and it comes up heads every single time, the probability of it coming up heads the next time is still 0.5. It is not changed by those previous flips. All right. Now that's different than saying, what is the probability of getting heads 11 times in a row when I flip a coin? That's different because you haven't had those first 10 rolls or flips. What I'm talking about is when you've already flipped the coin 10 times and you're saying, what's the probability of this next flip? Well, it doesn't matter what happened in those first 10 flips. The next flip is just likely to be 1/2. Just think about it. If it wasn't that way, you could totally game the system. You could just throw the coin at home by yourself and flip it like 10 times, and then it comes up heads 10 times in a row, so you're like, oh, it's probably going to come up tails next time. And then you could go bet somebody that like it's going to come up tails and you could win money. That's not how the world works, right? Every time you flip a coin, the probability of heads is 0.5, the probability of tails is 0.5. The coin does not have a memory. Each coin flip is independent. It doesn't affect those future coin flips. Okay. right? Whereas you can have dependent events. So for instance, let's take a deck of cards, right? So let's say that I take a deck of cards and I come up to someone in the class and I say, pull a card out and look at it, and you look at it. And then I say, okay, put the card back into the deck, and you do. And then I go to the next person and I tell them, pull a card out of the deck, and they do, right? And I could go around the whole room like this. Well, as long as we're putting the cards back each time, then all of those are independent events, right? The fact that you pulled out the ace of spades first doesn't mean that someone is less likely to pull out the ace of spades as we go around the room, okay? But what if I did this? What if I went to the first person in the room and said, pull out a card, look at it, and then just set it on your desk? And they go, okay. Well, then I go to the next person. The probabilities have changed, right? Because now there's one less card in the deck, and there is no ace of spades. So if the first person picks the ace of spades, what's the probability of person number 2 getting the ace of spades? 0, because it's already been removed from the deck, right? So you would have to recalculate. Let's say you were trying to get the ace of hearts, right? We just have something where we say, I'm going to go around the room. Whoever pulls the ace of hearts is the winner. You get an A on the test or whatever, right? This hypothetical situation. So the first person pulls out the ace of spades. Well, now the probabilities of getting the ace of hearts is slightly better for person number 2. Because there's one less card. There's still one ace of hearts in the deck, but there's now 51 cards to pull from instead of 52. And then that person do you see how that would work? If I went through the room like that, the probability of getting the ace of hearts gets better up until someone pulls the ace of hearts. Those events would be dependent. So that's what oftentimes is referred to as with replacement and without replacement. If I have a deck of cards and you pull a card with replacement, that means once you look at it, you put it back in the deck. Okay? If we do without replacement, that means you keep the card and you keep it on your desk. This is often, there's very, very typical problems that you see done in early probability problems with marbles. And you'll see people talk about, oops, my meeting just died here, although I don't think anyone's in the Zoom. But anyways, we'll set it back up. What was it? Sorry, the Zoom meeting just did something. Let me fix this. Right. So you'll have colored marbles in a bag, and then you'll have questions where they say with replacement or without replacement. With replacement means each time you look at the marble, you put it back in the bag. Without replacement means each time you take it out, you keep it. Okay? Because if you keep it, that changes the number of marbles in the bag. That changes the probability for the next round. You have to recalculate the probability for that next round. Okay, that's what that means. Right, okay. One thing they do in statistics a lot of times is if you're trying to do sampling in a statistical manner, then technically the way that you do that could come up in your probabilities. It could affect your probabilities, but sometimes it affects them in such a small way that we can ignore it. So let's say that I sent all of you out and I said, each one of you pick 100 people in Ventura and ask them if they support smoking on campus. So we're not even talking about students. We're just talking about people in Ventura, right? Well, it's very likely that each of you would pick a different 100 people, right? But it is possible we could get a little bit of overlap, right? Maybe 2 of you are cousins. You decided to take the class together or something. And then, you end up asking a couple family members the same question. Well, that technically should affect our probabilities. But if that only happens 1 or 2 or 3 times out of like 5,000 people, it's pretty negligible, right? It's kind of not going to affect things very much. So in some cases, it's such a small effect that we kind of get to skip that. But in general, we want to be aware to make sure that happens as little as possible. Let's see. Oh yeah, so then they start getting into the with replacement, without replacement. So just kind of keep that in mind when you're doing the homework. Okay, here's one that throws people off. Probabilities, you really have to pay attention to the wording, right? You want to have good reading skills. So read carefully, because it's like what we see right here. There's times where people are not reading carefully and they interpret the probability problem in kind of a sloppy way, and then they end up doing the wrong calculation. They can't figure out why, and then you'll explain, well, you're doing the calculation right for the way you're thinking about the problem, but the way you're thinking about the problem is wrong because you didn't read quite closely enough, which for probability, you have to read real close, because like one word different can mean a totally different probability that you're calculating. So for instance, let's look here. 2 different people are randomly selected from those in your class. Find the indicated probability by assuming that birthdays occur on the days of the week with equal frequencies, right? So we're just in a large enough set, you would have roughly equal distribution of people born on the days of the week. So listen to these 2 statements. Find the probability that 2 people are born on the same day of the week. Find the probability that 2 people are both born on Monday, right? So a lot of times those statements will be misconstrued because they'll say those are the same thing. And you'll say, oh, no, they're not the same thing. And they'll say, because if you're born on Monday, you're born on the same day of the week. So those are the same thing. You calculate them the same way. Now, because if your condition is that you're born on the same day of the week, that 2 people are born on the same day of the week, that could be they're both born on a Monday, or they're both born on a Tuesday, or they're both born on a Wednesday, or both born on a Thursday. See how you have 7 different possibilities for the first statement? Find the probability that the 2 people selected were born on the same day of the week. Whereas in B, you only have one of those options. Find the probability that 2 people are both born on Monday. All right, so how would you calculate this? You'd use that multiplication rule. What's the probability? Where am I? So the probability, because no particular day of the week is specified, the first person can be born on any of the 7 days. So if I pick 2 of you from this class, the first person was born on one of those days, right? They were born on a Monday, a Tuesday, a Wednesday, a Thursday, a Friday, a Saturday, or a Sunday. They were born on one day, okay? The second person, what is the probability that they were born on that same day? Well, there's 7 options. There's 7 days of the week, but there's only one way for them to be born on that same day. So it's 1/7. So the probability that if I randomly pick 2 of you, the probability that you were born on the same day of the week is 1/7. Okay. Now look at this second one. Find the probability that 2 people were both born on a Monday. Well, if I randomly select 2 of you, the probability that the first person was born on a Monday is 1/7. And the probability that the second person was born on a Monday is 1/7. So when we multiply those together, we'd get 1/49. That's a whole lot less likely, right? So do you see how these statements, although a lot of people interpret them to really be the same thing, are actually different? So you have to read very closely. Really ask yourself, am I interpreting this correctly? Because I'll see that where students read, but they don't read very well. Their probabilities are correct, but they did a different problem than the one presented to them. I mean, their probability is correct for the way they're thinking, but their thinking is wrong, is what I'm trying to say. You have to make sure you understand the problem before you dive into that. Okay, and then we haven't gotten into hypothesis testing yet. We'll sort of leave off right. Let's see. We'll start with this. We'll look at a few more applications of this multiplication rule when we look at next time. Okay, so we'll start up with that. So please make sure you're staying caught up on the homework. Make sure that you're working on those projects. If you have any questions, you're coming to me and asking me questions. You're welcome to come into Zoom right now and ask me questions. Otherwise, I will see you next week. Be safe. It's supposed to warm up here, so be ready for that. And then I'll see you next week. Okay, thanks, everybody.